The motivation for this project is to improve on standard OSPF functionality. OSPF is a routing protocol which uses link state algorithm to find the best path for packets to flow through the network. The best path is decided based on costs of the links in the network. OSPF uses a reference bandwidth of 100 megabits per second for cost calculation. The formula to calculate the cost is reference bandwidth divided by interface bandwidth. The links are assigned costs at the beginning before LSA flooding. These link costs are updated only in case of any change in the link speed. The best paths are calculated using Dijkstra's algorithm based on the calculated link costs. We propose to make this cost allocation dynamic and smart. To make this link cost allocation smart, we will assign costs to the links based on historical data. With the help of historical data, we identify paths occupancy. We will change the costs of the links such that the highly occupied paths will now have more cost, which makes them less probable in many path computations.
Let's understand the base case topology. We have two hosts A and B. These are in turn connected to 5 routers: router A, router 1, router 2, router 3 and router B. In this part, we run a trace route from host A to host B. We notice that it passes through router A, router 1 and router B. We first start by running traffic from host A to host B, which is UDP traffic. So we first notice that we have run TCP dump on all the router ports for listening to port 5001. We first start the IPUF on the client and the server. We notice that the IPUF traffic is seen on router A, router 1 and router B. In this part of the experiment, we congest the link between router 1 and router B. We then run IPUF traffic from A to B. We notice that traffic is seen on the interfaces of router 1, router A and router B. In this part, we check the routing table of all the routers in the topology. We see that all the routes which are included in the Quagga config file are shown in the routing table of each router. Next, we talk about the non-SDN case. It consists of two hosts A and B, which are in turn connected to 5 routers. But in this case, all the routers have an intelligence module internal, which learns the traffic on each of the links. We firstly look at the startup script initialization. So after initializing the startup script on each of the routers, we notice that each of the historical entries of the interfaces is 0. We then run a trace route without congestion on the links. So we run a trace route from A to B and notice traffic on router A, router 1 and router B. In the next part of the non-SDN case, we run iperf traffic from host A to host B. We notice that traffic is seen on router 1, router A and router B. We then move on to the next case where we have already loaded historical data into the interface of router 1 pointing towards router B and also on the interface of router B which is pointing towards router 1, as you can see in the captures. We then use this pre-run historical data as an open loop congestion of the link between router 1 and router B. After running a trace route, we can see that the traffic flows through a longer link or a longer path. We then run a trace route from host A to host B when the link is not congested. We notice that it flows through a shorter path, that is router A, router 1 and router B. We then run iperf in this congested link scenario. When traffic flows from router A to router B, we notice traffic on the longer link, that is router A, router 2, router 3 and router B, while nothing is noticed on router 1. We then demonstrate what happens when high traffic is predicted on the shorter path. It takes some time to converge, but after the convergence happens, the traffic flows as expected. We then move on to the SDN case. In the SDN case, we have the same 5 routers which are connected to each other, but to those 5 routers, a controller is connected. We also have extra test nodes just to check ping connectivity between hosts and to test throughput. We then run iperf when there is no congestion. So here we see traffic on router 1, router A and router B. Next case shows what happens when one of the links is congested in the shortest path. In that case, the hypo of traffic moves through a longer path, and over here that is via router A, router 2, router 3, router B, and then to host B.